So I have the basics of the ray box intersection working. Basically, what that looks like is for every pixel, there's an x and a y offset. The vertical being the y and the horizontal being the x. So there's some point in space that you're starting from, and you're shooting a whole bunch of rays, like um, kind of like a screen door kind of idea. All those separate squares being the pixels and stuff. They're all going into this space, and when the code sees that they hit the block, it's going to color the pixel that's related to that ray. In this case, just with some random color. It's green is the absolute value of the y offset, and red is the absolute value of the x offset. So, with 0 being in the middle, then you're getting more and more positive x offsets are this way, and negative x offsets this way. And again, positive and negative for y as well. I set up an FPS counter, which I thought was kind of cool. It tells you the average over the past 32 frames with this little graph. The you'll see the average kind of takes a second to normalize, but yeah, and I'm not sure why it's different when you run it from the other terminal, but it's in any event, this is where we're at. The code is very similar to the previous raycasting versions of this project. We've got an x offset and a y offset that are calculated from the glfrag coord, which is the fragment coordinate on the x and the fragment coordinate on the y. And there's uniform variables passed in that are the width of the screen in pixels, the height of the screen in pixels, a theta, which controls the side-to-side rotation, and a phi, which rotates their it's a sort of vertical rotation kind of idea. And the scale is like a zoom factor. Here scaling the block based on, or the x and y offsets. So the point where you're starting from doesn't actually change. You're just kind of reducing the side to side and up and down offsets to make it so that you're not going to clip into the block. You're not actually changing where you're starting from. There's no perspective like divergence and stuff. It's an orthographic projection. But this if x offset and y offset were if the rays diverged more, if I changed the direction with the x and y offsets, that would constitute a the rays would diverge, and you'd be looking at something where you'd have like a perspective projection kind of idea there. But basically, so I established the origin with the x offset and the y offset, starting at just some value out the z axis, so that I make sure that okay, yeah, I figured this out. Just wrote it all out on a whiteboard and stuff. But based on the Pythagorean theorem, you can get the fact that if the cube is from -1, -1, -1 to 1, 1, 1 on each axis, it's from -1 to 1. The corner, any given corner to the origin is about 1.75. So putting your starting point at 2 makes it so that you're never going to clip into the corner or anything. even if that corner is pointing directly at you, it's only coming out 1.75 units, or 2 units out that axis. So it's I think that's a good way to handle it. The direction this could is basically just pointing in the opposite direction, so it's pointing to the origin from your starting point. Well, I say to the origin, but it's really just this for the centermost pixel. It would be very close. Well, centermost pixels, I guess, because it's an even number, but essentially it's pointing directly towards the origin for the centermost pixels. And then I have this rotation up. So initially you're rotating above. You're rotating up first, and then you're doing your side-to-side rotation. The reason for that is I'm rotating about the x-axis, and I would have to, I'd have to multiply this by this rotation matrix, this theta rotation matrix, in order to be able to do the phi rotation. So it's another multiplication to do it that way. So I'm doing it in this order, basically rotating up and then rotating about the y-axis to do the side-to-side rotation, because it's not different after you've done this phi rotation. So the origin and the direction are rotated by that phi, so it's after this operation you're looking at something that is either pointing up or down or flat if that value is 0. And then after this rotation is applied, then you're looking at something that's it's been moved left or right. In terms of rotation, you've spun it side to side. Then check and see if a ray with that origin and that direction hits the box. And I was thinking about this earlier. I could probably change this from mat 4 to mat 3 and just do this with 3 component vectors. The only reason it's 4 is because that's a mat 4. This is just some code that I got from this guy, Neil Mendoza. But I'm looking at this and I'm seeing that it's 0001, so it's the component of the identity there, and then it's the zeros on that last column as well. So I think it's relatively trivial to convert it to mat 3s and then just have these be vec3s, because I'm only using 3 components of the vector for this operation, and so you see if I do hit it, I am using the absolute value of the x offset and the y offset to set the red and the green channels. Otherwise I'm discarding it and you get the clear color in the background. So this hit code is adapted from some C++ code that I found, and I'm not 100% sure how it works, but it's it does exactly what I need it to. I set the minimum and maximum values here, and so right now I'm setting X resolution, Y resolution, sending that across. Phi and theta are being set by sinusoids. Yeah, and it's this SDL get ticks, which is like tells you how many milliseconds have passed since the beginning of the program. So at this point, this is actually the largest project I've worked on in terms of just the number of files involved. It's not crazy or anything, but it's just a lot of balls in the air, I guess. They the mgui stuff, that's the I'll go ahead and walk through that really quick in a minute here, but it provides this really nice interface for just setting up a GUI really simply. It's the so when I've got this up, I can go to the draw menu, hit sphere, and then I set the radius. I set where I want it on the X, where I want it on the Y, where I want it on the Z, whether I want to draw it, whether I want to mask it, and then I've got a button to draw it. I set the color, set the alpha, and that gets sent across. Similar with Perlin noise, this is going to be there's going to be more to that. Triangles, it's 3 points, so you set where you want each point. And again, drawing and masking and the color. The ellipsoid, you've got XYZ location, XYZ radius, XYZ rotation. So then you've got cylinders, which is located by a point in the center of the top and a point in the center of the bottom. And then again a radius to set the thickness of that. And so again, this is all done with the MGUI library. This is all the variables are kept. They're static variables, so they're it's retained. It's everything's declared inside the function call, but it's retained between calls to that function. So it's actually a really nice setup for this. This tube thing is a radius with it's a cylinder with another cylinder cut out of the center. You have an inner radius and an outer radius. And also I should mention with this, you hit Control on any one of these and you can type in a value. And this is very hard to use. It's not really that practical at all. And I'll probably drop it at some point, but it's just I don't know. It's more powerful than the other sort of cube shape that I have here. This is basically you set a maximum value on the x-axis that you want, minimum value on the y-axis, or maximum and minimum on each x, y, and z. Set a color. Tell it whether you want it to draw or mask or both, or neither. But honestly, if it's neither, then it's pretty useless. You might as well just not do that. This height map thing is basically going to have it so you generate a height map with different algorithms, and then send that to the GPU as a 2D texture. And then you have like a vertical scale that would let you make it taller or shorter. Blur is going to be like a configurable radius. And it's basically just going to average values based on the neighborhood. Then clear all is it's a clear that respects the mask value of all states, or of all cells rather. So if that cell is masked, it's not going to overwrite with zeros, right? Then in the utility menu, there's a reinitialize, which does override the previous values of the masking. And again, a load save thing here. You enter your file name, and then you tell it you want to load it or save it. And some just kind of information there. The cellular automata I'm going to try and do to where you have like single updates basically. You could do it where it's going to be live updates just kind of every time that the thing, every new frame or whatever, but I don't know, it's a lot of computation basically. The the static lighting or per frame lighting, I also should add the ambient occlusion calculation here, which basically darkens things based on what's in its neighborhood. Masking, so you can unmask all cells. You can toggle the mask value for every cell, or you can mask by color, and that's not implemented yet. But basically what that's going to look like is I set some R value, some G value, some B value, and then you set like the range for each of those. So mask everything that's within some certain range of the red value I set, or the blue value, or the green, etc., etc. Also the alpha channel, but the so getting to the point where I don't actually have the texture declared yet, so that's going to be held here. The handlers are held there, and then the setup is going to be part of this initialization of the GPU data. This has been an interesting one for me. I've never actually broken out all the functionality of my code this way before. But to go through the whole thing really quick, main is literally just the declaration of one of these Voraldo objects, and the constructor is this thing that sets the current menu state. It creates a window, sets up the GPU data, and the GPU debug stuff, and while you don't have it set to exit, it calls this really long function. It's called draw menu and take input. Draw menu and take input is a very long function. It's something like 1,100 lines or something, but the way it's done, it switches based on a current menu state, and then it goes to some label. So it's really only doing a small amount of code each pass when you do call it or whatever. It's only ever doing like this much. So it's nothing crazy. It's long. The whole function is long, but then the input handling is here at the bottom. So if you quit, if you close the window, if you hit the escape key, you're basically, if you're on the main menu, you exit. If you're on one of the first level menus, then you go back to the main menu. If you're on one of those third level menus, you go up to whichever the associated second level menu is. So it's just kind of logically you go up one level when you hit exit. So there's going to be more controls. The like the rotation and stuff, I'm going to be controlling that with the arrow keys. The scaling, I'm going to control that with the plus and minus. So these are going to be things that are upcoming, but the gist being that all the stuff that draws into the 3D texture is going to be implemented as compute shaders that operate on every voxel in the texture. So for a sphere, each invocation of that shader is going to have knowledge of the center point of that sphere and the radius of that sphere, and it checks it against the location in that range. So this is really coming along. I'm right at the point where I'm gonna start writing the compute shaders. I have some example code to work from. So that's going to be a hopefully not too big a deal to get that working. I'm not currently declaring the textures, but I have done it before in this slice object class. Or am I wrong about that? That's actually it's in the same class. So yeah, here it loads a texture, and then binds that texture to the texture 3D thing here. The binding point for the texture 3D textures, basically, and it makes it an image. I'm gonna have to review this, but basically, the idea here is that this is a read-write texture that operates on the values are 8-bit per channel, so it's red, green, blue, and alpha, and you use an integer vector to reference that. So this is the shader associated with that other project. It's let's see. Yeah. So this IVEC is it's an integer vector, and that's what you use to load from the image. So yeah, we're getting there. This is really coming together, and I think having the GUI is going to be kind of a big deal in order to make it more accessible, make it just kind of make sense to people more, because it's kind of nebulous, and if you've, I don't know, this 4250 final, the way it works is basically you uncomment one of these textures, you just pick one, and then you start the program, and it'll show you that. And if you're using one of these ones, you can do cellular automata updates on that image data. That's a different shader. I was calling it a fake compute, but basically it's just well, I invoke a whole bunch of those, so this compute thing, I just called draw arrays with that program, that fake compute program shader bound, and so when you draw it, it's actually doing an operation where it reads from the current image object and writes to the next image object, and then it binds the other one. So it's just something I had it where it would trigger based on like a key press. But it's going to be triggered through the GUI now. So it's really coming together, I think.